Hello everyone, Mr. Hine, and today we're looking at 3 for 1, which is differentiability. Pretty big word, give it 2 stars. All right. And this lesson and this video are just meant to talk to you about what it is. All right. So the informal definition of differentiability is just another word for that the derivative exists of a function f of x at every x value. So that's the informal definition, is if we look at a function f of x, the derivative will exist at every x value. Now, other ways you can think about that rather than using the word derivative is you can think about it as, the slope of the tangent lines. Or if I want to get even more informal to help you understand this, the derivative is really just the slope at each moment in time. Remember when we talked about the IROC, the instantaneous rate of change. So I'm talking when you're given a function f of x is differentiable if the derivative, if the slope exists every single moment along that function. Now, the formal definition of differentiability is 2 parts. All right? So a function f of x is differentiable if 1, the function f of x is continuous, and 2 is if the derivative exists. All right. And that's what it means to be differentiable, are these 2 things. Remember, definitions are very important in math, and that's how we prove things. Now, what does it mean for a derivative to exist? What does this mean? Because we've talked about what it means to be continuous. Continuous, there's the 3 conditions. Right, the 3 conditions. So hopefully you remember those, refresh your notes on those. Now, what is the derivative by definition? Right, the derivative by definition, recall that f prime of x, the derivative, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Right, that's the definition of the derivative. Now, for a function to be differentiable, we're saying f prime exists. Now, notice that we're looking at a limit. Well, when do limits exist? So that begs the question, when do limits exist? And we talked about this before when we talked about continuity. Right? When do limits exist? Well, limits exist if what it approaches from the left is the same as what it approaches from the right. And I know I mixed up my hands there. I don't know what it looks like from your angle. So what this means is that for f prime to exist, so f prime of x exists, what that means is that the limit as, now I'm going to use a different definition here. I'll stick with your definition. I'm going to change it up, and we're going to use a different definition of the derivative, a different version of it to help understand this. So f prime of exists if, basically, if we use the definition we use, is the limit as h approaches 0 from the left. So if we approach 0 from the left, here's a little graph to help you visualize this. You have an arbitrary curve, f of x, and we want to evaluate the slope, the derivative at x. Well, you can pick a point that's h away to its right, x plus h, or you can pick a point that's h away to its left, right? So if we want to know if the derivative exists at x, by definition, that means that the limit from the right and the limit from the left of the derivative have to exist. So I guess before I even start using the h's, if f prime exists, let's just write that the limit as x approaches some value c for, say you want to find the derivative at c, from the left of f prime of x is equal to the limit as x approaches some value c from the right of f prime of x. Or in my example, what I'm using is I'm calling this c, right, that point c. Right. Now, if we use the definition that we're used to of the h's, here's how it might look. So we'd be saying the limit as h approaches 0 from the left, so we're approaching x from the left, then it would be f of x minus f of x minus h over h. And that has to equal the limit as you approach from the right, which that would be using x plus h minus f of x over h. And that's what it means to be for a derivative to exist, is to show that the left derivative is equal to the right derivative. The slope from the left side is going to approach the same slope as you approach from the right side. Now, in the next video, I'm going to talk about a different definition we use here, where I'm just going to cover it here, and then you'll see in the next video. Where basically, for an arbitrary curve f of x, whatever it looks like, instead of using the x minus hx and x plus h, and that's a really comfortable definition to use that we've used for a while, the other definition we're going to use is a different method you saw, where if we want to evaluate the derivative at a point c, then what we do is we would look at the limit as x approaches c, and we have two values, say an arbitrary value x to its left and an arbitrary value x to its right. So limit as x approaches c from the left of f of x, so this would be the point x comma f of x, and that's the point c comma f of c, just to help you understand that. So this definition here would be as you approach that value from the left, f of x minus f of c over x minus c equals the limit as x approaches c from the right of f of x minus f of c over x minus c. So keep in mind, I know I realized I wrote these the same way, and that's okay, because remember, you can approach a slope any direction you want as long as you go from the same point to the same point. So I went from f of x to c, and I went from x to c, and that's okay. If I end up doing a slope backwards, like if there's a positive slope and I go backwards, well, then it would just be negative over a negative, which would still result in a positive, so we'd be okay. So that is the formal definition of derivative for a function to be differentiable, is that it has to be continuous and that the derivative has to exist. Now, an informal way to think about it is just think that the derivative exists at every point, which is really just the slope at each moment exists. Okay. Whatever helps you understand it is important, and maybe you even have your own way of understanding it. So a function is differentiable if it is continuous and the derivative exists. Now, don't be confused. There's a few things that that things get confusing with. Right. So notice that the definition, so just to reiterate, the definition of differentiable is a function f is differentiable if 1, f of x is continuous, and 2, f prime of x exists, which implies that the limit as you approach from the left, because the derivative is a limit, f prime of x will equal the limit as you approach from the right of f prime of x. Okay. Now, the one thing I want to talk about here, and where I'm going to go with this, is I know I already talked about this, is we're saying if a function is differential, if this is true. So it's going in this order. Or, I'm sorry, if a function is differentiable, then f of x is continuous and f prime of x exists. Now, note some interesting things here is we can't work backwards. A function that is continuous need not be, and I just feel like using that language, but doesn't need to be differentiable. So just because you're continuous doesn't mean you're differentiable. An example is the absolute value function. And we're going to be exploring this in the next lesson, not this lesson. All right, and you'll see why that's not differentiable. But f of x is continuous, and you could test the three conditions if you want. But f prime of 0 does not exist because it's a corner, which again, the next video we're going to show you and talk about why corners are a reason why differentiability doesn't work. Right? Which implies that f prime of x does not exist. Okay? So that's the first note, is a function that's continuous doesn't need to be differentiable. The second note is if a function is not continuous, so if you're not continuous, then that function is also not differentiable. And I'm going to do a quick run through this. I know you have a problem where you're going to explore this too. Right? But if a function is not continuous, we can say the function is not differentiable. Now, why is that? Now, let's look at the three conditions and say if they all fail. So let's say condition 1 fails for not being continuous. So condition 1 would say that the limit as you approach some value c of the function f of x does not exist. If I look at a simple graph here, where you have this right here, we can see that condition 1 fails. It's not continuous because the limit doesn't exist from the left and from the right are not the same. Now, why is this function not differentiable? So if we look at the slopes from the left and right, so again, this means that the limit as you approach some value c from the left, the slopes from the left will not equal the slopes as you approach from the right, the derivative as you approach from the right. So let's say we call this c right here, and the function's there. Okay. Now, if we look at the slopes from the left, as we approach from the left, notice that the slopes here of the secant lines, as we get closer and closer, all these slopes are 0. But as we approach from the right, that slope is not 0. That has a negative slope. M is some negative value. And as we approach even closer, what ends up happening is M ends up becoming, the slope ends up becoming negative infinity, or even as you get really close, well, since we can't equal that value, it'll be very close, in which you'll see that's why it's negative infinity. So you can see here that f prime of x does not exist since the limit as we approach c from the left does not equal the limit as you approach that value from the right there. Okay. And notice again, we're talking about the slopes though, not the function. So that's if condition 1 fails. What about condition 2? So what if condition 2 fails of continuity? And condition 2 fails would say that f of c does not exist. So if I give you a visual of it here, you have a curve, and it has a hole at some value c. All right. Now, why is the function not differentiable here? Is recall that the definition of f prime of x is the limit as x approaches some value c as we get closer and closer to that value from some value x that's x that's a distance away. Right? So we want to evaluate the limit at c, the slope at c, and we're going to evaluate the slopes and get closer and closer from some arbitrary value x, closer and closer to c. Right, so that's the definition I'm using, not using the definition with h. But what's the problem here is this does not exist since f of c does not exist. Right? In order to use this definition, we would have needed f of c, but there's a hole at f of c, right? There's a hole at x equals c. So we can't use that definition. But that's why condition 2 failing would show not differentiability. And the last one, what if condition 3 fails? An example of this. Right, so now we have a hole, so the limit still exists, and then we'll put a function right here. So the limit exists, there's a value at c, but they don't equal each other, in which condition 3 fails of continuity. Well, if we look at the slopes from the left and right, so as we approach from the left, notice that the slopes are tending towards negative infinity, because again, we're looking at the slope between a value on the curve and the value at that point c comma f of c. So the slopes as we approach from the left are tending towards negative infinity, but as we approach from the right, if I do solid lines, notice as we approach from the right, those points are tending towards positive infinity. And you can see right there, using the definition of differentiability, that the limit as you approach from the right of the derivative tends towards positive infinity. So that's why if a function is not continuous, f is not differentiable. And you can hopefully visualize these and re-put together these pictures if needed. Okay. So that covers differentiability, the meaning of it, and looking at some notes and just making sure you understand that it doesn't work both ways. Right? If a function is differentiable, then these two things occur. So we can work in this direction. But just be careful of trying to work backwards, because if a function is continuous, that's not always differentiable, right? But if a function is not continuous, we do know it's not differentiable. So a lot of confusion there, and you just have to remember this. If you remember the definition, you can always go back and make sense of things, okay? Now, before I wrap this video up, there is one more topic that you're going to start exploring in this lesson, okay? And that is the topic of antiderivatives. Note the anti in front there, anti. So we've learned what a derivative is. We can look at the definition, but really derivative is the instant rate of change. It's the slope / rate of change at a particular moment, at a specific moment. Okay. And we usually denote it as f prime of x. For a function f of x, the derivative will be f prime of x. Or we might denote it as dy dx or y prime. All different ways of writing the derivative. And you can keep taking derivatives to analyze the rate of that and so forth. Now, what's an antiderivative? And the notation they use for it is a function f of x. And notice the notation on antiderivatives is we use a capital F. Is an antiderivative of a function f of x if, when you take the derivative of the antiderivative, you return back to the function f of x. All right. And that notation might confuse you, but imagine it just going backwards. So if you had f of x and you wanted to find the rates of it, to go from a function f of x to its derivative, we take the derivative. And I'll show you an example of this. So to go from a function to analyzing its rates, its slope function, we take the derivative. Well, an antiderivative would be working backwards. So that would be, we take the antiderivative of f prime of x. So if you take the antiderivative of f prime of x, then you return back to its original function f. The notation gets interesting because with what I'm saying here, this then takes on f of x if we're looking at this top definition up here, right? The derivative, well, that's not quite true. I don't want to confuse you. This doesn't take on f of x. We take the antiderivative function and we get a function that we call the antiderivative, where if we take the derivative of that function again, we'll return to where we are. Now, I might have lost you. Let's just look at examples, and that will hopefully clear things up, because even me, as I'm going through, I'm like, losing myself. All right, example. So let's take the antiderivative. And then after we take the antiderivative, it's important, and your work is telling you to do this, it's important to check your answer by taking the derivative of it. So say, for example, we have a function f of x equals 3x squared. What's the antiderivative of this? So remember, antiderivative, we're working backwards now. Well, recall that with derivatives, we always subtract 1 due to the power rule. So with antiderivatives, we're going to add 1 here. So that's going to become 3. The question is if we take the derivative of this, 3 times what is going to take us back to 3? In which, if you just solve for that what, like that spot where you're saying 3 times what is going to get us back to there when you take the derivative, when you divide by 3 to both sides, I'm just going to write it as 3 over 3 for now, which then I'll simplify and say I think the antiderivative is 1x to the third. Well, let's check our answer. So if we take the derivative of this function, the derivative of our antiderivative, do we get back to where we were? So the derivative using the power rule would be 3 times 1, which is 3x, and then minus 1 squared, which is the case. So in that case, we found the antiderivative. Awesome. All right. Let's look at another example. So let's say we have a function that equals 5x to the 7th. So what's the antiderivative of that? Antiderivative of that, well, we know it's going to have to go to the 8th because we're working backwards, so now we're adding 1. And then we ask ourselves, and you might pick up on a pattern, but I'm not going to explain it to you yet. So we ask ourselves, well, if we take the derivative here and use the power rule, 8 times something is going to have to equal 5. So what's that something have to be? Well, if we divide by 8 to both sides, we know it has to be 5/8. And there we go. Just like over here, I was 3 over 3. Over here is 5 over 8. Okay. And if we check our answer, take the derivative of that. Well, if you bring that to the front, 8 times 5/8, the 8s would cancel, you just be left with 5, and then subtract 1, and we're back where we started, so we know we did it correct. All right. So that's what an antiderivative is. The notation with the definition gets kind of funky. Just recognize that antiderivative is working backwards. So you're working backwards. And what's that mean? So let's note. So an antiderivative, this is the last thing I'm going to say in this video. I know it's getting kind of long. Antiderivative. So a derivative, let's start here. Derivative finds the rate, finds the slope function or the rate of change. And then you can keep taking derivative, and then it's the rate of change, and so forth. So derivatives, you find the rates. Antiderivative is working backwards. So if you think about like acceleration, distance, or distance, velocity, and acceleration, derivatives would go from distance to velocity to acceleration. Antiderivative would work backwards, where you are kind of reversing this, reversing the derivative towards, earlier rates of change, to eventually an amount of something slash, distance. Because eventually, if you work backwards enough, you're going to be at that value. All right. Oh, sorry. Before I wrap this video up, I did make one mistake up here, and I'm going to have to highlight in red. I did make one big mistake. I made a big mistake, and I wonder if anyone caught it. And I almost ended my video. This is not true. Nor is this true. And you're probably thinking, why, Mr. Hein? That makes perfect sense. You check your answer. How is that wrong? Well, remember that if we take the derivative of the antiderivative, we get back to where we started. But what's the derivative of a constant? Of a number. Remember that the derivative of a constant is 0. So in our equation here, when we took the derivative of our antiderivative, how do we know that there isn't actually like a +1 at the end, or a +2 or a +3? How do we know that there's not something there? Or am I saying that right? I think that might be +0. Yeah, because we know that there's +0 here. Well, that means that when we took the derivative of the antiderivative and there's a +0, what we're missing up here is how do we know that there wasn't some constant c? Because when we take the derivative of a constant c, you're at 0, right? So this right here with the plus c is the true antiderivative. Same thing over here. It was not 5/8 x to the 8th. It was 5/8 x to the 8th plus c. And that is big. And I apologize for missing that. I forgot that was part of this lesson. Because that changes the whole game. Now that's going to change the functions you look at. Now notice why I say plus c and not a number. Well, what can c be? So note, what can c be? Well, it's any constant, any number, right? Any constant which is, a real number. And if I want to show you that, take a look. So let's look back at this problem. And this is getting messy, but and I thought we were almost done. I almost missed one of the biggest things. So we already showed you that the antiderivative of 3x squared is going to be x to the third plus c. All right. Well, let's check with different numbers. What if we check with the derivative of the antiderivative, and let's say that we make that a 1. So the derivative of x to the third plus 1. Well, notice the derivative of x to the third would be 3x squared. Well, what's the derivative of 1? Remember that the derivative of any constant, that rate's not changing. They're staying at 1. So that's plus 0, which is 3x squared, which is the function we originally had. So we would have said, oh, yeah, x to the third plus 1, that's an antiderivative. But did it have to be plus 1? What if we would have made it, plus 10? Does that change anything? The derivative of x to the third plus 10 is 3x squared, but the derivative of a constant is 0 again, so that's also 3x squared. So the idea here is we need the plus 3, so how many different antiderivatives are there? Or there's infinitely many antiderivatives because of the plus c. And that's very big, and I apologize again for missing that the first time through and making this video even longer than it is. Okay. So you're going to have to mess around with it. You're going to have to do a few problems yourself, make sense of this yourself, because you can see it. Now we're getting into these derivatives, antiderivatives, working forwards, working backwards on all this new language, and you just have to make sense of it yourself. If you have any questions, I'm more than happy to listen and help elaborate on what you're thinking.